Hey there, and welcome to this explainer. Today, we're basically stepping into the shoes of a microscopic detective to crack the chemical code. Have you ever stopped to wonder how scientists actually figure out the exact chemical structure of a totally invisible, completely unknown substance? Well, we're going to dive deep into the awe-inspiring power of mass spectrometry, specifically how chemists determine precise molecular formulas using some brilliantly clever analytical techniques. Think of this whole explainer as a forensic mystery. But instead of looking for fingerprints left on a glass, we're hunting down subatomic signatures left on the molecules themselves.
So let's just jump right into this really intriguing problem. Imagine you're at a chemical crime scene. You've isolated your suspect molecule and you put it on a standard molecular scale. The scale spits out a number. Your molecule weighs exactly 60.1 grams per mole. Case closed, right? Actually, scratch that, it's not even close to being solved. Standard weighing just doesn't give us enough clues. Because as it turns out, in the chemical world, multiple completely distinct molecular suspects can weigh exactly the same on a standard scale.
Low-resolution mass spectrometry creates this sort of weight illusion. Take a lineup of 4 entirely different molecules: propanol, ethylenediamine, acetic acid, and urea. These things have wildly different properties, different structures, and different elemental makeups. Yet, if you calculate their masses using whole numbers, which is what we call the nominal mass, they all share the exact same weight of 60.1. If you only had a basic low-resolution mass spectrometer, all 4 of these distinct molecules would give you the exact same identical signal. The trail would literally go cold right there.
So what's the fix? Well, the crucial point here is that we absolutely must move away from the whole numbers of nominal mass and utilize something a lot sharper, which is precise mass. You see, nominal mass uses weighted chemical averages, like just rounding carbon to 12. But the precise mass? That takes the actual exact mass of an element's most common isotope, stretched out to several decimal places. By zooming in on the mass to that extreme degree, we can finally shatter this illusion and tell our molecular suspects apart.
The ultimate solution is running our mystery sample through a high-resolution mass spectrometer. When we do that, we don't just get a simple 60.1, boom, we get 60.05754. This instrument acts like a highly calibrated molecular scale that gives us pinpoint precision down to 5 decimal places. By matching this incredibly exact number to our list of suspects, we can definitively prove that our molecule is, for sure, C3H8O. The other formulas, they just simply don't match those decimal points.
What's truly staggering here is the sheer scale of precision we're talking about. High-resolution mass spectrometry, or HRMS for short, boasts an accuracy of about plus or minus 0.005%. To put that into perspective, your standard chemical methods for finding molecular weight are only accurate to about 1%. These highly specialized, incredibly expensive HRMS machines are so precise, they just completely eliminate the alibis of all the other molecular formulas. It really makes it a definitive, open and shut case.
But let's be totally realistic for a second. Not every lab has the budget for $1 million high-resolution machine lying around. So if you're stuck with a standard low-resolution scale, is the trail just dead? Absolutely not. Chemists have developed a really genius workaround to find the exact molecular formula using clues that are literally hiding in plain sight. Instead of relying on that extreme decimal precision, we can interrogate what's known as the molecular ion cluster. When a molecule is blasted with high energy and detected, it doesn't just form one single lonely spike on the graph. It forms a whole cluster of peaks. Why? Because nature actually leaves these rare, natural signature stamps on molecules in the form of heavier isotopes. By analyzing the entire cluster of peaks, we can figure out exactly what atoms make up our mystery molecule.
To really wrap our heads around this, let's interrogate carbon. In nature, atoms aren't purely just one weight. While almost 99% of carbon exists as your standard carbon-12, a tiny but incredibly predictable 1.08% exists as the slightly heavier carbon-13 isotope. That means if you have a massive sample of molecules containing carbon, statistically just about 1% of those carbon atoms are going to be exactly 1 mass unit heavier.
And because of that 1.08% natural abundance of carbon-13, we get this highly predictable secondary signal called the M+1 peak. M is your main molecular ion, and M+1 is simply the version of that molecule that randomly grabbed a heavier isotope from nature. This acts just like a subatomic fingerprint. By looking at the size of this M+1 peak relative to the main peak, we can actually calculate exactly how many carbon atoms are hiding inside our suspect molecule.
Let's look at a really concrete example to see this in action. Propene and diazomethane both have a nominal mass of 42. They're completely indistinguishable on a basic low-resolution scale. But check out their M+1 peaks.
Propene has 3 carbons, so its M+1 intensity is roughly 3 times that 1.08, giving us 3.34%. Diazomethane, on the other hand, only has 1 carbon, so its M+1 peak is much smaller, hovering at 1.87%. By simply doing the math on these isotope ratios, we can easily tell these two molecules apart entirely based on the intensity of their M+1 peaks. No expensive high-resolution equipment required, just some really clever arithmetic.
And it goes way beyond just carbon. We can hunt for other isotopic clues too. Some elements naturally have isotopes that are 2 whole mass units heavier, creating what's called an M+2 peak. For instance, a larger than normal M+2 peak is very often the very first hint to a trained chemist that sulfur or silicon is hiding out in the compound. That's because sulfur-34 sits at an impressive 4.4% natural abundance. It's kind of like finding a highly specific, custom brand of tire track left right at our crime scene.
Okay, now let's dive into the most dramatic isotopic fingerprints of them all, the halogens. While carbon and sulfur leave these tiny, subtle little peaks, chlorine and bromine, they absolutely kick the door down. They create massive, unmistakable M+2 signals in a mass spectrum that are virtually impossible to miss. Chemists affectionately refer to these as the halogen doublets.
Take chlorine, for example. It naturally exists in a roughly 3-to-1 ratio between its lighter isotope, chlorine-35, and its heavier isotope, chlorine-37. If your mystery molecule contains just a single chlorine atom, your mass spectrum will show your main peak and then another peak 2 mass units higher that is exactly 1/3 the height. It leaves a very distinct, unavoidable fingerprint on any molecule it attaches itself to.
And bromine is even more striking. Its 2 isotopes, bromine-79 and bromine-81, occur in almost a perfect 1-to-1 ratio in nature. This means if a molecule has exactly 1 bromine atom on it, the mass spectrum is going to show 2 massive peaks separated by 2 mass units, standing side by side like identical twin towers. You literally can't miss it.
Now, when multiple halogens decide to join the party, this pattern recognition becomes practically a superpower for chemists. When you mix 2 bromines, or maybe 3 chlorines, or a wild combination of both, the math just compounds. You can visually identify the distinct clusters of M, M+2, and M+4 peaks, depending entirely on the exact mix of those atoms. By just glancing at the shape of these peak clusters, a trained chemist can immediately go, yep, we have a molecule with exactly 1 chlorine and 2 bromines.
Let's step into a real-world crime scene, so to speak, just to see how completely obvious this bromine signature is in a live mass spectrum. When you process a sample in the lab, the data isn't just a boring list of numbers. It forms a visual landscape that you quickly learn how to read.
Check out the data for ethyl bromide. Notice those striking doublets sitting way over on the far right at masses 108 and 110? See how they are practically identical in height? That near-equal intensity separated by exactly 2 mass units is the definitive smoking gun. It proves, beyond any shadow of a doubt, the presence of exactly 1 bromine atom attached to our ethyl radical. Literally no other element does exactly that.
So to finally wrap up our little investigation here, the chemical detective's workflow is wonderfully systematic. First, you determine the basic nominal mass. Second, if you're lucky enough to have the budget, you check for the precise mass via high-resolution mass spectrometry down to that glorious 5th decimal place. But third, if you don't have that machine, you rely on clever isotope pattern recognition, analyzing those M+1 and M+2 ratios to reveal the true molecular blueprint.
I really hope this explainer has shown you the awe-inspiring power of mass spectrometry. I mean, we've gone from a totally ambiguous weight of 60.1 all the way to finding exact atomic structures just by reading isotopic fingerprints. It really leaves you to wonder, knowing how these totally invisible subatomic patterns reveal a molecule's true identity, how do you think these exact microscopic detective tools are being deployed right this very minute to solve complex mysteries in modern drug discovery, environmental testing, and forensic science? The clues are always there. You just need the right tool to read them. Thanks so much for joining me on this explainer.